So we're going to start looking at now proving identities. We've done some work with simplifying trigonometric expressions using known identities. So now we're going to prove identities. We're going to do it algebraically. We're going to understand the difference between proving and verifying an identity. And then we'll show that verifying that the two sides of a potential identity are equal for a given value is insufficient for proving an identity. So we will verify and prove more complex trig identities using the skills we've learned from previous lessons. Some useful hints when trying to prove an identity are listed below. So the first thing you have to remember is that it is not permitted to move terms from one side to the other, nor can you square or square root both sides of an identity. The whole point of these exercises is that we're trying to show that the two sides are equal. So it's not an equation, it's an identity, and you want to show that the two sides are equal. You can only move things from one side to the other if you know that the two sides are equal, if you have a definite equation, right? Same thing, you can only take the square root of both sides if you know that you have an equation, if you know that the two sides are equal. But that's the whole point of these exercises. We're trying to show that they are equal to each other. So you cannot move things from one side to the other. You can't take the square root of both sides or square both sides. You have to work down either the left side of the identity or the right side of the identity or both sides to get the same expression on both sides. That is the whole point of what we're going to be working on. And there have been questions on diploma exams in the written response where a student is asked to prove an identity. Okay? So there's a chance you could be tested on this on the diploma exam. So some hints. Normally we begin with the more complex side first. If possible, we use known identities that are given on the formula sheet. For example, that Pythagorean identity would be one example of things that are on the formula sheet. And these Pythagorean identities will be used normally when you look and you see that you have squares of a trig function. Sometimes you might need to change all trig functions or trig ratios to either sine or cosine. For example, you might replace tangent with sine over cos, or you might replace secant with 1 over cos. Sometimes you might have to factor to prove an identity. If there is a sum or difference of fractions, write as a single fraction, which means you're going to get a common denominator to allow you to do that. Occasionally, you may need to multiply numerator or denominator of a fraction by its conjugate. So we're going to see examples of all of these. So to review some steps that you're going to use. The first thing I would look for, if there are no powers, put everything in terms of sine and cos, which is what part 3 tells us to do. If there are no powers anywhere, put everything in terms of sine and cos. If there are powers, specifically power 2's, look to those Pythagorean identities that are on the formula sheet. Okay? Usually begin with the more complex side first. If there's powers other than 2, chances are you're going to have to factor, which is what hint 4 does. Okay? If there's a sum or difference of fractions, so if you have two terms that are added or subtracted and you've got different denominators, well, then you have to find a common denominator to allow you to combine those. So those are some of the hints that we're going to be looking at in order to do this. Okay, Logan? You with us? All right. So example number 1 says, consider that statement. So first we want to show that it is true for a specific angle, the angle pi on 3. So the left side is 1 over cos x, so we're going to have 1 over the cosine of pi on 3 minus the cosine of pi on 3, and that must equal the sine of pi on 3 times the tangent of pi on 3. So we're going to use our unit circle values to find out what each term is equal to. And at pi on 3, you might remember that the coordinates are 1/2, comma, root 3 over 2, and that the tangent is root 3. So the cosine of pi on 3 is 1/2. So that first term will be 1 divided by 1/2 minus the cosine of pi on 3, which is, again, 1/2. So dividing by a fraction is the same as multiplying by the reciprocal. So this first part would be 1 times 2 over 1, or 2 minus 1/2. And 2 is 4/2 minus 1/2, which is 3/2. So that's what the left side works out to, 3/2. So we need to get the same thing on the right side. The sine of pi on 3 is root 3 over 2, times the tangent of pi on 3, which is root 3, or root 3 over 1. And when you multiply root 3 times root 3, you'll get root 9, which is 3 over 2 times 1. So we got the same thing on both sides. We get 3/2 on both sides. So we've shown that this identity, or this statement, is true for a specific value of x being pi on 3. We can use our graphing calculator to show that the statement is probably an identity. So again, the difference between a statement and an identity is an identity tells us that it is true for all values, all permissive values of the variable. We just showed that the statement is true for a specific value of the variable, pi on 3 radians. The graphing calculator can be used to show that it is probably an identity. Now, the reason the word probably is used there is because we're going to put both of these, both sides of the statement in our graphing calculator. So in y1, we'll put the left side. I'm going to have to use brackets here to keep that first term together, which is 1 divided by the cosine of x. Close the bracket on the x, close the bracket on the 1 over cosine of x, minus cos of x, that's the second term of the left side. And that needs to equal the right side, which is sine x times the tangent of x. So we're going to show that these two graphs are the same. However, they're only going to be the same for whatever windows we choose. So I am in degree mode, and that's fine. So for my windows, I'm going to go from negative 360 to positive 360 degrees along the x-axis with a scale of 90. I'm going to go from negative 10 to positive 10 on the y-axis, and I'll use a scale of 2. So the reason I chose those windows is that one of the terms of this statement is tangent of x. And remember, tangent goes up and down forever. Sine and cosine only go up to positive 1 and down to negative 1. But we've got some other terms there. We've got a 1 over cos x. Well, that's secant x, and we haven't really looked at the graph of secant x to see what it looks like. Okay? And on the right side, we have a factor of tan x, which again, tan x goes up and down forever. So that's why I chose the y min and max that I did. So it happened really quickly, but the two graphs are the same. I graphed the first one in blue, the second one in a different color directly over top. So again, this just shows that the statement is probably an identity. And again, the difference between a statement and an identity is that an identity is true for all permissive values of the variable. Our non-permissive values here, you can see that you've got asymptotes, and it is going to ask us to state the restrictions in Part D, so we'll get to that. But you can see that you have asymptotes there, and those asymptotes come from the fact that tangent is one of the factors. And tangent has a vertical asymptote at 90 degrees, at 270, at negative 90, at negative 270, and every multiple of 180 degrees. So again, the calculator shows us that the statement is probably an identity. But that's only restricted to whatever domain we've chosen, from negative 360 to positive 360 in this case. It is possible that there is a place somewhere outside that domain where the two graphs are not the same. And that is the why that the word probably is used. But now we're going to prove the statement is an identity using an algebraic approach. So that's what the main focus of these next 2 days are going to be on. Okay? Proving that the identity, or proving the statement is an identity using an algebraic approach. So if we start with the original expression again, which is 1 over cos x minus cos x, and that has to equal sine x times tan x. So basically we want to work down, in this case we're going to probably work down both sides to show that we get the same expression. Okay, so on the left side, remember, if there's no powers, we put everything in terms of sine and cos, which we already have here. On our list of hints, we're also told that if you have the sum or difference of terms, combine them into one term by getting a common denominator. So this cos x is the same as cos x over 1. Right now I have two different denominators. My first term has a denominator of cosine x, the second has a denominator of 1. I'm going to get a common denominator there, and that common denominator will be cosine x. So the first term won't change, but the second term, which has a denominator of 1, I would need to multiply top and bottom by cos x to get a denominator of cos x in that term. So multiplying the bottom, the 1 by cos x gives me cos x. The top, when I multiply by cos x times cos x is cos squared x. So I've got a common denominator here. The numerator will be 1 minus cos squared x all over my common denominator of cosine x. I'm just going to open up a formula sheet here. Okay, do you remember from yesterday, what does 1 minus cos squared x equal? Sine squared x, right? And that comes from the Pythagorean identity. The fact that sine squared theta plus cos squared theta equals 1. And we said that there's two variations of that. You can subtract the sine squared theta from both sides and get cos squared theta equals 1 minus sine squared theta. You can also subtract the sine squared theta from both, or the cos squared theta from both sides, and saying that sine squared theta equals 1 minus cos squared theta. And that's what we're going to use here. The fact that 1 minus cos squared theta is sine squared, in this case it's x, over cosine x. So that's what we have on the left side. We want to get the same thing on the right side, which we can get by taking the tan x and writing it as sine over cos. That's one of the hints that we had. Put everything in terms of sine and cos. And now when you multiply these, remember it's top times top, bottom times bottom. Sine x times sine x is sine squared x over 1 minus cos x. Now we have the same expression on both sides. We've shown that this statement is an identity because we show that we can write them as the same expression on both sides, which proves that the statement is an identity for all values of x except they're non-permissive, which is what we're going to do next. What are the non-permissive values? So if we look at the work that we did in part C, we want to look and see where do we have denominators. Okay, we have denominators of cos x for both terms on the left. And if we go back to the original one, we have 1 over cos x. So cos x cannot equal 0. And also, when we change tangent to sine over cos, we got a second statement with cos x in the denominator. So this is where our restrictions will come from, wherever the cosine of x equals 0. If we look at our unit circle, the coordinates here are 1, 0. There the cosine is 1. At 90 degrees or pi on 2 radians, the coordinates are 0, 1. That's where cosine is 0. Negative 1, 0 at 180. So there the cosine is negative 1. And at 270, the coordinates are 0, negative 1. The cosine there is 0. So at 90 degrees and at 270 degrees, that's where the cosine is 0. And every multiple of the period from there, you're also going to have non-permissive values. So we would say here that x cannot equal, and if I write it in terms of radians, x cannot equal pi on 2 plus n pi, where n is an element of integers. There's our restrictions, which we can verify on our graphing calculator. If I go into the trace mode, x equals 0, you have your y value returned there. Y equals 0, so that's not a restriction. If I go to the other graph, the other equation, which was sine x times tan x, again, 0, 0 is part of that graph. If I go skip to 90 degrees, now you see I don't have a y value returned. For the first graph, what about the other equation? Again, no y value is returned. If I go to 270 degrees, again, no y value is returned on the first equation. On the second equation, if I let x equal 270, again, no y value is returned. I can check negative 90. For the second equation, no y value returned. For the first equation, no y value returned. So I can use my graphing calculator to verify my restrictions, my non-permissive values. Okay? All right. So on the next page, we want to do something similar. Here we have a statement, sine x over tan x equals cosine x. We want to show that that statement is true for an angle of pi on 6. So we're going to have the sine of pi on 6 divided by the tangent of pi on 6, and that should equal the cosine of pi on 6. So at pi on 6 on the unit circle, the coordinates are root 3 over 2 comma a half, and the tangent was root 3 over 3, which you get by going sine divided by cos. It was 1 over root 3, which became root 3 over 3. The sine of pi on 6 is 1/2, and that's divided by the tangent of pi on 6, which is root 3 over 3. To divide by a fraction, we multiply by the reciprocal, so that'll equal 1/2 times 3 over root 3. That gives us 3 over 2 root 3, or 3 root 3 over 6, or root 3 over 2. When you rationalize by multiplying top and bottom by root 3, the bottom will be 2 times root 3 times root 3. Root 3 times root 3 is 3, times the 2 gives us the 6, which is what the cosine of pi on 6 is, root 3 over 2, right from the unit circle. So we've shown that the statement is true when x equals pi on 6. We can use our graphing calculator to show that the statement is probably an identity by seeing that we get the same graph for both sides of the statement. So the left side is sine x, close the bracket, divided by the tangent of x. The right side is just cosine of x. If we graph them, we get the same graphs. So it shows that the statement is probably an identity because it only shows that the graphs are the same for the windows that we chose, between negative 360 and positive 360 degrees. It is possible that there is a spot outside that domain where they're not the same, which is why to show for sure we have to prove them algebraically. So we need to show that sine x over tan x is equal to cosine of x for all values. So the right side is just cosine of x. There's nothing we can do for that. We need to work down the left side to show that it is also equivalent to cosine of x. So there's no powers here. So we're not going to look at Pythagorean identities. We're not going to factor. We will put everything in terms of sine and cos. So the first factor, or the first part of that, was sine x. That's being divided by tangent of x, which we can write as sine x over cos x. And again, to divide by a fraction, you multiply by the reciprocal. Dividing by sine over cos is the same as multiplying by cos over sine. And the sine x's will cancel, and we are left with cosine of x, which is what the right side is. So we've shown that the two sides are the same. We've shown then that the statement is actually an identity for all values of the variable except the non-permissive ones. Now, in this case here, our non-permissive values will come from the left side. The right side is just cosine x. There's no denominator there. But the left side has a denominator of tangent of x, right? We've got sine x divided by tangent. And the tangent is sine over cos. But neither of them can equal 0 because tan x is a denominator. If the sine x equals 0, you're going to have 0 over something which is 0. Can't have that because tan x cannot equal 0. And if the cos x equals 0, you're going to have sine over 0, which is undefined. So because tan x is a denominator, neither sine x nor cos x can equal 0. Which means every multiple of pi on 2. Right? If we look back on the previous page, at pi on 2, that's where the cosine is 0. At pi, that's where the sine is 0. At 3 pi on 2, that's where the cosine is 0. At 0 or 2 pi, that's where the sine is 0. And we've said that neither sine nor cosine can equal 0, so therefore x cannot equal n pi over 2, where n is an element of integers. And we can verify that on the graphing calculator by going into trace. And I need to be, for this case, I can only be on equation 1 because equation 2 is cosine of x that has no restrictions. If I let x equal 0, which I default to, there is no y value returned there. So that shows that 0 is non-permissive. If I let x equal 90, again, no y value returned. 180, no y value returned. Negative 90, no y value returned. Negative 180, no y value returned. So this verifies that our restrictions are every multiple of 90 degrees or every multiple of pi on 2. I wrote them in terms of radians, but I could have wrote them in terms of degrees as well. It doesn't matter. We're not told one way or the other. So again, this is what we're going to be spending the next 2 days on for most of it. Showing that a statement is an identity. Using those hints that we were given at the start. Only using a specific angle only shows that the statement is true for that specific angle, not all angles. That's why we have to do it algebraically. So for this next one, we want to show that sine x times cos squared x plus sine cubed x is equal to 1 over cosecant x. So on the right side, 1 over cosecant, well, that'll just be sine. You see, cosecant is the reciprocal of sine. So 1 over cosecant will be 1 divided by 1 over sine. Cosecant is 1 over sine. And to divide by a fraction, you multiply by the reciprocal. So you multiply by sine over 1, which is sine. The right side is sine x. So we need to get sine x on the left side as well. And if we look at the left side, you'll notice that there has a term with sine x and cos squared x and a term with sine cubed x. As soon as you see higher powers that are higher than 2, you're normally going to have to factor, which in this case, we can take out a common factor of sine x on the left. Common factor of sine x on the left gives us with cos squared x plus sine squared x inside the bracket. And what does cos squared x plus sine squared x equal? It equals 1 from the Pythagorean identity. Sine squared theta plus cos squared theta equals 1. So this will be sine x times 1, which is sine x. And we're done. We've shown that the two sides are equal. We've shown that this statement is an identity. Most of them can be done in a couple fairly straightforward steps. You're going to look at that list of hints that you were given. That'll guide you what your first step should be. Most of them, though, can be done in 2 or 3 fairly simple steps. Okay? If you're asked to prove an identity, it can be proven. It can be done. You try something. If it doesn't work, you try something else. But most of them can be done in 2 or 3 fairly simple steps. Some of them will take a few more steps, but they can all be done. So this next one is going to take a few more steps, but as we work through it, we're going to see it's just algebra. The left side, sine A plus tan A all over 1 plus cos A must equal the right side, which is 1 over cotan A. In this case, we're going to work down both sides. Most of our work is going to be down the left side. But let's start by working down the right side first to simplify that. The right side is 1 divided by cotan A. And cotan A is cos A over sine A. To divide by a fraction, you multiply by the reciprocal. So instead of dividing by cosine over sine, you're going to multiply by sine over cosine, which gives us sine over cosine. And we could write that as tangent if we wanted to. For now, I'm just going to leave it as sine over cos. And now I need to work down the left side. I need to make the left side also become sine over cos or tangent. All right. If we look at the left side, there are no powers there. So we can't use any of those identities. We can't factor either. So the hints told us that if there are no powers, put everything in terms of sine and cos. So that's what I'm going to do. That Top is sine A, which is sine A over 1, plus tangent, which is sine A over cos A. And that is all divided by 1 plus cos A. One of the hints said that if you have two terms with different denominators, get a common denominator. So you can combine those two terms. So that's what I'm going to do here. I'm going to get a common denominator of cosine A so that I can combine these two terms into 1. So this 1, I'm going to multiply it by cosine A, and then I'll multiply the top by cosine A as well. So that top will be sine A cos A. The second term won't change because it already has a denominator of cosine A. But by multiplying the top and bottom of that first term by cosine of A, I now have a common denominator of cosine A. So I can write them together as one expression. And again, we can't forget that is all divided by 1 plus cosine A. So I'm going to continue working my way down that left side. The right side is sine A over cos A. We need to continue to work down the left side to also get sine A over cos A. So what I'm going to do now on that left side, on the top, I'm going to take out a common factor of sine A. The first term is sine A cos A. The second term is just sine A. Each of those terms has a common factor of sine A. And so when you take that out, you're going to have cos A plus 1 all over cos A, and that's all divided by 1 plus cos A, which is 1 plus cos A over 1. And the reason I wrote that as a fraction is because the top is a fraction. I have one fraction divided by another. We know that to divide by a fraction, you multiply by the reciprocal. We've seen that several times. So I'm going to change it to that. I've got sine A bracket cos A plus 1 all over cos A. Instead of dividing that by the fraction 1 plus cos A over 1, I'm going to multiply by the reciprocal. I'm going to multiply by 1 over 1 plus cos A. And now we have a factor of cos A plus 1 on top and a factor of 1 plus cos A, which is the same as cos A plus 1. Those cancel. And you are left with sine A times 1 over cos A times 1. You are left with sine A over cos A, which is what the right side is. So you're done. Most of these can be done in 2 or 3 fairly simple steps. This one took a few more steps, but it's just algebra. You're doing the same thing with trig functions that you've learned how to do with numbers. You found common denominators for fractions and added them together. Instead of dividing by a fraction, you multiply by the reciprocal. You've done that lots with fractions, numerical fractions. Now you're just doing the same thing with trig expressions, fractions that involve trig functions. It's the same process, same procedure. You're just doing it with trig functions instead of fractions. Okay? So some of them will take a few extra steps, but it's just algebra. So you take your time, do it methodically, and you'll get there because they can all be done. As I said, you try something. If it doesn't work, you try something else. So when I was in university, I took a course called Euclidean geometry, and it was just these massive proofs. And some of them would take like pages to do. And you'd look at them and you'd try something and it didn't work, so you tried something else. And I live in an apartment across the street from a 7-Eleven. Sometimes I would actually leave the apartment, go down and get a slush, come back, give my mind a break, and I would try something else. And eventually I'd get there. But you have to persevere. You try something. If it doesn't work, you try something else. And I've told this story to my students for years now. And it's funny because I still get emails from students that say, hey, I was in this course and we had to do these proofs. And I did what you said. I took a break. I went and did something else. Maybe not go get a slush at 7-Eleven, but I did something else. I gave my mind a break. And then I came back and I got it. Okay? So try something. If it doesn't work, you try something else. You've got those hints to work from. They can all be done. Try something. If it doesn't work, you try something else. Okay, so on this next one then, we want to show that the left side equals the right side. Normally we work down the more complicated side first, which in this case would be the left side. The right side is cosec squared x. I'm going to leave it like that for now. You do know that cosecant is 1 over sine. So you could also write that as 1 over sine squared x. And we might have to do that. But for now, I'm just going to leave it as is. So on the left side, I've got that statement, right? And we're going to see that there's often more than one way you can do these. And that's fine. You don't always have to do them the same way. So for this one, I'm going to show you there's possibly two ways that it can be done. So as soon as you see those squares, that should trigger your mind to look at the Pythagorean identities. Okay? So I've got sec squared x on top and sec squared x minus 1 on the bottom. If you look at the Pythagorean identities, this one here involves secant squared. 1 plus tan squared theta equals sec squared theta. Well, just like there's variations for the original Pythagorean identity, meaning you can bring, let's say, the cos squared theta over to the right and say sine squared equals 1 minus cos squared, you can do the same thing with the other Pythagorean identities. You could say that if you've got 1 plus tan squared theta equals sec squared, you could say that tan squared theta equals sec squared theta minus 1. You could take that original identity and subtract 1 from both sides. And why would you want to do that? Well, because the denominator of this is sec squared x minus 1. So we've just seen that that's the same thing as tan squared x. So you're going to have sec squared x divided by tan squared x. And at this point, probably what I would do is I would put everything in terms of sine and cos. That's one of the hints that we were given. Sec squared is 1 over cos squared x. And that is divided by tan squared, which is sine squared over cos squared. So if I continue working my way through, we've said that the right side is cosec squared x. On the left side, instead of dividing by a fraction, we're going to multiply by the reciprocal. So instead of dividing by sine over cos, we'll multiply by cos over sine. And we've seen this many times. We can cancel factors that are common on the top and the bottom. We can divide top and bottom by cosine squared x. They cancel, and we'll be left with 1 over sine squared x, which is cosec squared x. And we're done. Okay, we are done. Now, as I said, there is often more than one way you can do these. So if I take that original identity and let's paste it to a new page here. Let's see that there's another way that we could do this. This one is going to take a few more steps, but it'll work. So again, I'm going to leave the right side as cosec squared x. And in this case, what I'm going to do is I'm going to, instead of using the Pythagorean identity, which is the easiest way to do this, but instead of doing it that way, what if we just changed everything in terms of sine and cos? So sec squared x would be 1 over cos squared x. And that is divided by another sec squared x, which is 1 over cos squared x minus 1. Some of you might be wondering, why can you not just cancel the secant squared x to start with? Well, if you did that, you're going to get 1 over negative 1. But the point is, you cannot do that. You cannot cancel part of a binomial. Okay? If you say that you want to cancel sec squared x on top and bottom here, what you're really saying is if you had expression like 2 over 2 minus 1, you're saying, well, I can cancel the 2's. And I'm left with 1 over negative 1, which is negative 1. And that's not correct. If you simplify the original expression, it's going to be 2 over 1, which is 2. That's what that equals. If you cancel the 2's, though, you're going to gain 1 over negative 1. It's not correct. You cannot cancel part of a binomial. Okay? So, if we follow the rules that we've established here, I'm going to combine these two terms together by getting a common denominator. So I'm going to have 1 over cos squared x divided by, my common denominator here will be cos squared x. This 1, the second term, would be 1 over 1. I want to write that with the denominator of cos squared x, which means I'd have to multiply bottom and top by cos squared x. So this one here isn't going to change because it has the right denominator of cos squared x. But here I'm multiplying top and bottom because I'm writing 1 as 1 over 1. And I'm multiplying top and bottom by cos squared x. So that'll become cos squared x over cos squared x. And that allows me to combine the two together to get 1 minus cos squared x all over cos squared x. What does 1 minus cos squared x equal? Well, that'll be sine squared x. That's from our Pythagorean identity. So 1 minus cos squared x is the same thing as sine squared x. And instead of dividing by a fraction, I will multiply by the reciprocal. So I'm going to multiply by cos squared x over sine squared x. The cos squared x's cancel, and you're left with 1 over sine squared x, which is cosecant squared x. So there's another way that one could have been done. It took a few more steps, but it works. And for some of these, there is more than one way to do them. You try something. If it doesn't work, you try something else. You use those hints that you were given. If there's power twos, normally the easiest way to do those is look to the Pythagorean identities. But in this case here, like I showed you, there's another way it could be done without using the Pythagorean identities. If there's powers higher than 2, normally that means you're going to factor. Sometimes if you've got fractions that are being added together, you need to get a common denominator, which we did here. And we've done it in a couple other examples as well. You try something. If it doesn't work, you try something else. They can all be done. Okay? They can all be done. So, we're going to stop there. We're going to do some more of these tomorrow. And then on Monday and Tuesday, we're going to be doing some solving equations using trig identities. Okay? As I wrote on the board, you're going to have your Chapter 6 quiz on Tuesday, and your trig exam is going to be on Thursday. So Wednesday, we'll go through the Chapter 5 and the Chapter 6 quiz, and you'll have time to work on the review. which I've sent out for photocopying. So I'll run down and see if it's there, and I can give that to you so you can start working on it. Just like your Unit 1 review, that is the best thing you can do to help you get ready for your test. You need to have the review done before you write the test, and you need to understand and know how to do everything on there. If you do understand and know how to do everything on there, you're going to do fine on that test. But that is the best thing that you can do to prepare for that test on Thursday. So I can't emphasize enough how important it is that you actually do that. Okay, so we're going to leave the solving equation part for, again, Monday and Tuesday. Tomorrow we'll do some more work practice with using these trig identities to do other identities. So there is an assignment there that you can start working on. It says do questions 1 through 4. I will post these on Google Classroom so you can check your answers. So the first page is 1 and 2. The second page is 3 and the start of 4. 4 goes on to the next page though. E and F. So you're going to stop after E and F on number 4. Tomorrow we'll see some examples where you use conjugates in order to help you prove an identity. So again, I will post the solutions to Google Classroom so you can check your answers. It's important that you do these though. The practice is important. It's going to help you for the quiz and the test.